Hello and welcome to this second session. My name is Dr. Aditya Abhyankar, and in this particular session, we'll be predominantly talking about wavelet transform. We all know that wavelets, they have become a buzzword, and many believe that if last 100 years were the 100 years of Fourier transform, the coming 100 years are going to be the 100 years of wavelet transform. And what is so special about wavelets? Why wavelet transform is so radically different than all the conventional transforms that we were using for last 350 odd years? And one salient feature that really distinguishes wavelets from the rest of the transforms is the ability to zoom in and zoom out. And that's why we have titled today's talk as Wavelet Transforms Ability to Zoom In and Zoom Out. So let's get started. I honestly believe that it is the ability of the wavelet transforms to zoom in and zoom out that makes them very special. And in today's session, we are going to look at the detailed mathematical treatment to really understand this power of wavelet transforms. We all appreciate the very fundamental idea of wavelet transforms. And we know that there is something very special about wavelet transforms, and that is the ability of wavelet kernel to dilate. And so if we pose this question, can conventional kernels or basis functions dilate? And the answer of this question is no, not really. And if we think that, then what kind of analysis a typical conventional transform, let's say Z transform, which is a very useful, very popular transform in discrete or digital domain. So if we pose this question, what analysis can a Z transform do to a system? Then let's look at a quick demonstration as to what information Z kernel can provide about the system. This particular demo gives an insight into the capabilities of Z transform and positioning of poles and zeros. This is modified from Lorentz, and I had modified this long back in 2007. So this is the plot. We have pole zero plot and then impulse response and then pole location and zero location, the mathematical formulas, and the magnitude response and the phase response. Let's bring the attention point to zero frequency. And now we can place the poles and zeros at different location. We know that if the poles are inside the unit circle, then the impulse response is converging. As the poles, they start moving towards the unit circle, it becomes more and more divergent and it becomes oscillatory. And the moment the poles go outside unit circle, the impulse response becomes divergent and the system becomes unstable. That's why it's important to keep the poles inside unit circle. So such kind of visualization helps students to realize the importance of the position of poles and zeros. You can also create notch filter by having poles at equal angles. If they are kept at real axis, it's possible to create a quick low pass filter like this. And if the positioning of the poles is moved to exactly 180 degrees opposite, the low pass filter becomes high pass. This is again an example of notch filter. The low pass high pass action happens because of the x of z and x of minus z kind of an effect. So positioning of the poles is quite critical, and you can create notch filters of this kind pretty quick and fast. Similarly, positioning of the zeros is also very important. If the zeros are placed inside unit circle, the phase of the filter is minimum phase and phase is delay. If the zeros, they move outside unit circle, then the phase of the filter is maximum, which essentially means that the system will be sluggish and it will have slow responses because of the maximum phase. That's why in design, it's good to select the zeros which lie inside unit circle just to make sure that the phase is minimum phase. So we saw the ability of Z transform to do so many things with the system. Z transform can tell us whether my system is stable, how to make my system fast by placing zeros inside the unit circle and making my phase minimum phase. Z transform can also make sure that my system is rational. That means the system transfer function is a ratio of two polynomials with finite degree. I have finite number of poles, finite number of zeros, and using poles and zeros I can also create the stop band and the pass bands and the corresponding filters. So all in all, Z transform is a very powerful tool, no doubt about it. We can also make sure that Z transform ensures that my system is causal. And one way of looking at this is we make sure that there is no pole at Z is equal to infinity, and that will ensure that the Z is equal to infinity is part of the ROC, and that ensures that my system is causal. So all these underlying concepts are very deep and very important. However, the main question still remains, and that is, can my Z kernel dilate? And the answer of this question is no. In spite of all these conventional kernels being very powerful, they lack this ability to dilate. And most of the real life signals are sometimes slow moving and sometimes they are fast moving. And that's why this ability of kernel to be able to dilate is extremely important, and we are going to touch upon that today. In simple language, the ability of kernel to dilate essentially means the ability of kernel to either squeeze or expand. It can squeeze if I'm talking about a part of the signal which is fast moving, for example, and can expand if I'm talking about a slow moving part of the signal. And so this ability of kernel to either squeeze or elongate, it really matters, and that is exactly what we intend to bring out in today's session. In my opinion, this is exactly the reason why most of the modern frameworks are indeed scalable, because of this ability of the underlying kernels to dilate. I'll just give you a quick example. When we search for images using Google search, for example, what gets retrieved back is thumbnails. And when we click on that thumbnail, the entire image of bigger resolution gets pulled out and retrieved back. So this is a good example of a scalable system. The thumbnail is a low resolution representation, and the entire image or a higher resolution image has a different resolution. So we want to have information, same information, at different resolutions, at different scales. And this is useful in so many practical day-to-day examples, applications. And that's why this scalability plays a very important role, very vital role in the entire schema. Now let's understand wavelet transform. First of all, we should understand that for all the conventional systems, we often talk about just one single filter. But in wavelets, we talk about filter bank, because there are two separate series that we make use of for decomposing the signal that we are trying to process. The single series, and this is responsible for giving us the scaling function, or the double series, which is responsible for giving us the wavelet function. Now we also know that the scaling function is also sometimes called as father function, and as we know, it is a low pass filter. And this wavelet function is also sometimes referred to as mother function, and as we know, it is a high pass filter. So it's a combination of mother and father, or low pass filter and high pass filter, or scaling function and wavelet function, we end up producing the entire family of that particular mother wavelet kernel. The basic idea of wavelet MRA, so this MRA stands for multi-resolution analysis, is very powerful, and it essentially tells us that you select any mother wavelet. For example, her mother wavelet is depicted over here, and using this one single function you can represent or construct any other signal or function which is either continuous or discrete. How do we do that? We typically use three operations, and I call these three operations as hallmark features of wavelet transform. Let's see them. The first operation is what is known to us as scaling operation, and scaling is magnitude scaling. So it's just that we are changing the magnitude of the kernel. This is the simplest of the three operations, and the remaining two operations are equally important, wherein we invoke the underlying property of the systems being time invariant, so we can shift our signals and still it will not have any impact on the final outcome. And now comes the important parameter. This S is the parameter which is responsible for letting our kernels dilate, either expand or squeeze. So these two operations, which are what are popularly known to us as translation and dilation. So this is my translation parameter and this is my dilation parameter. So scaling, translation and dilation together, they work and they can actually result into construction of any signal using just that one single wavelet kernel. And that is the power of wavelet basis function or kernel function. So what is so striking about this is resolution by resolution, you can keep on adding the details and you may end up generating a very high resolution representation of the underlying signal, which is not possible with the conventional transforms. And that's why you can actually bring in the resolution step by step to any level of detail. And what do you mean by any level of detail? We are going to study the dyadic structure, and very soon it will be clear what do we mean by any level of detail. And typically one analogy is quoted in many books. It is just like an onion that we can peel off shell by shell. So similarly in wavelet transform, we create different shells of different resolutions, and we can either add these shells and that will add those details so the overall representation becomes finer, or we can peel off those shells and the overall representation then becomes little coarser. It's quite possible, and this is the ability of wavelet transform. And how is this achieved? Once again, this is using dilation and translation, which is shown over here. And obviously the dilation is responsible for giving us the resolutions, and translation, it helps us move from one resolution to another resolution. So if I want to move from one peel of this onion to another, I need dilation because I'm changing the resolution. But if I want to move along the periphery of one single resolution, then what I really need is translation. It is as simple as that. This is a quick example wherein one particular signal is approximated using different window sizes. For example, this is one window size. As against that, this is a smaller window size. And you can clearly understand as the window size keeps on reducing, the representation of the signal becomes better and better and better. And these windows are called as dyadic windows because I can have 1 upon 2 to the power 1, which is half, then 1 upon 2 to the power 2, which is 1 by 4, 1 upon 2 to the power 3, 1 by 8, and this continues 1 by 16, 1 by 32, and you can imagine 1 over 2 to the power 100. So a very small window, and this will keep going on and on and on. And that's why Stephen Mallat says you can go tantalizingly close to the actual signal. And this is the power of wavelets. The resolutions can be added or they can be subtracted, and you can have very fine resolution representation or very coarse level representation of the signal depending upon what kind of application you're trying to build. Now let's understand the maths. Better said than done. Now if we really want to understand the nitty-gritties and understand how this is done, we need to understand the mathematics which lies beneath. And let's introduce the concept of linear space. Linear space is collection of functions, and any linear combination essentially ensures that the representation still remains in the same space. Such kind of space is typically what is known to us as linear space. And being linear, we can use any linear operation for any particular function which is projected in that space. So linear operations like adding, for example, or multiplying by a constant. And let's start by giving this space a name. And let's call this space as the fundamental space, let's say V of 0. And how do we understand this linear space V0? Well, we can say that the window of analysis is on this particular range, and the size of the interval for doing the analysis is 2 to the power 0. So in space V0, the window of analysis is 2 to the power 0. And then we can extend this notion for the next subspace, which will be V1. And we can say that in V1, the window of analysis or the size of the interval is going to be 1 upon 2 to the power 1 or 2 raised to minus 1. So in V1, the window size is 2 raised to minus 1. And similarly for V2, it will be 2 to the power minus 2. For V100, it will be 2 to the power minus 100. And we can generalize, and then we can imagine some subspace Vm wherein the window of analysis will be 2 to the power minus m. As simple as that. A quick example of this would be, you can clearly see that x dot, which is a function of some independent variable, it belongs to subspace V2. Now because it's V2 subspace, the window of analysis will be 2 to the power minus 2, which is 1 over 4. And you can clearly see that one single window of operation is only 1 by 4. And this confirms that this is a projection in subspace V of 2. Now if we see this particular example, and if I pose this question that this particular function, let's call that function as x of dot, it belongs to which subspace? Well, we can see the interval. For example, the interval is of duration 2, and because it is 2, so the length of the duration is 2, which is 2 to the power 1, and so I can always write this as 2 to the power of minus 1. And it goes without saying that this is my space. So I can very well say that this belongs to V of minus 1, isn't it? And so V of minus 1 will have a window size of 2, V of minus 2 will have window size of 4, V of minus 100 will have a window size of 2 raised to 100, and this goes on and on. So all the V minus subspaces, they have larger and larger window of operation. All the V positive subspaces, they have smaller and smaller window of operation. So the concept is very simple. And this essentially results into nested subspaces. So these are what are known to us as the nested subspaces. So V of minus 2 is a subspace of V of minus 1, which is a subspace of V of minus 0, which is a subspace of V of 1, and this continues. As we keep moving up the ladder, which is this particular direction, as we keep moving up the ladder, window size keeps on reducing, and eventually we say that we are moving towards the L2R norm. And similarly, as we keep moving down the ladder, that means in this direction, window of analysis keeps on becoming larger and larger and larger. So it goes without saying that we typically say that the representation becomes coarser and coarser and coarser, and eventually this is the result of moving down the ladder. And as we move up the ladder, then it results into L2R norm. So this is approximately equal to L2R norm because there is a closure which is required, but we can, for the time being, just to keep the thing simple, we can say that as we move up the ladder, we eventuate into the L2R. Okay, so we have understood the concept, but how exactly wavelet kernel helps us to move from one resolution to another? And unless we solve a problem, unless we unleash the underlying mathematics, we may not be able to get the complete feel of how we move from one resolution to another. So let's do that exercise now. Let's take a very simple example. And this particular function is shown over here. Let's call x-axis to be x, and then y-axis becomes f of x. It becomes function of some independent variable x. And as you can clearly see this function, it is exactly same as x between 0 and 3. So in this particular range. So mathematically we can write down this function as f of x is going to be equal to x when x is between 0 and 3 and it is 0 elsewhere, because it is really 0 after 3 and before 0. And that's why mathematically we can write it down this way. And now if we say that phi t is my father function or scaling function, and similarly psi of t is my wavelet function, and using scaling function being a low pass filter, I can calculate the projection of the same function f of x into v of j subspaces, and correspondingly using wavelet I can find out the corresponding projection in w of j subspaces. Can I come up with a neat mathematical framework to understand how do I change the resolution? And the answer of this question is yes. So let's put down the mathematical framework now. We typically say that for function f of x, this function f of x, it belongs to some subspace v of j, and the window of analysis is going to be equal to 1 upon 2 to the power j. The scale of operation for this would be 2 to the power j by 2 into phi of 2 to the power j x minus k. So this is the span of operation, and then we can always write down fj of x to be equal to summation over all the k values, because k is my translational parameter, and then alpha of j of k into 2 to the power j by 2 and phi of 2 to the power j x minus k. And these alpha values are the approximation values, since we are working with phi, which is our scaling function or low pass filter. And then formula for alpha jk will be integral from minus infinity to plus infinity fj of x into 2 to the power j by 2, and we'll use the same kernel 2 to the power j x minus k into dx. So this is the framework for the scaling equation or the scaling function. Now similarly, let's write down the framework for the wavelet function, and let's say the same function we will call it as gz of x. It would belong to some subspace w of z, and the window of analysis will be 1 upon 2 to the power z. I'm purposely using some other color, and the span of operation for this will be 2 to the power z by 2 into psi of 2 to the power z x minus k, where k is once again the translational parameter. And now this gz of x can be written as summation over all the k values and beta of z of k into 2 to the power z by 2 psi of 2 to the power z x minus k. And these beta values are the details, because now the filter that we are making use of is wavelet filter or the high pass filter, and these beta values can be calculated like this. It will be now integral from minus infinity to plus infinity g of z of x into 2 to the power z by 2 into psi of 2 to the power z of x minus k into dx. So this is the complete framework for wavelet filter. And as we have put down the complete framework, let's now put together our objectives, what we want to achieve. And the first objective that we want to achieve is to calculate f0 of x, which belongs to subspace v of 0. The second objective is to calculate g0 of x that belongs to w0. The third objective will be then to calculate f1 of x, which belongs to v1. And then the fourth objective will be to show that when we add v0 orthogonally into w0, it eventuates into v1. So this orthogonal summation is also something that we intend to bring out. Let's also figure out what phi and psi we intend to use for achieving all these four objectives. And let's say we want to keep the things simple for the time being, and we will make use of Haar scaling and wavelet function. So the phi of x in case of Haar typically looks like this. It will be 1 between 0 and 1, and it will be 0 everywhere else. And we also know how psi typically looks. So it looks like this. It will be plus 1. So this is my psi of x. So for values of x between 0 and half, it will be plus 1, and between half and 1, it will be minus 1. So this is the nature of phi and psi filters. You can now clearly see, you can think of phi to be made up of two halves which are 1 and 1. So this is like a moving average filter with a window of 2, and so it's clearly a low pass filter. And as far as psi is concerned, the first half is positive, second half is negative, so plus 1 and minus 1, so it's a differentiator. So it's clearly a high pass filter. Now let's work towards achieving our first objective, and that is to calculate f0 of x, which belongs to v0. So what we are saying is our z is 0. So our window of analysis will be 1 upon 2 raised to z. That is 1 upon 2 raised to 0, that is 1. So our window of analysis is going to be equal to 1. So if we go back to our original signal, our window of analysis will be from 0 to 1, 1 to 2, and then 2 to 3. So we will require k, that is translation from 0, 1 and 2. Keeping this in our mind, now let's understand the f0 of x by plugging in the values into the formula. So we have already seen that f0 of x will be summation over k values from 0 to 2 alpha zk, alpha 0k, because j is 0, so alpha 0k into 2 raised to j by 2, but j is 0, so 2 raised to 0, which is 1, so it's gone. And then phi of 2 to the power jx, 2 raised to j is 0, so 2 raised to 0 is 1, so phi of x minus k. So this is how our f0 of x will typically look. And now it goes without saying that k varies from 0 to 2, so we need to calculate all the three values of alpha 0 0, alpha 0 1 and alpha 0 2. So let's first of all calculate the first alpha value, and we know that f0 of x is looking like this. So we'll come back and we'll plug in the values of alpha on this slide. So first of all, we will calculate alpha 0 0. So j is equal to 0 and k is also equal to 0. And we know the formula. It is integration from minus infinity to plus infinity f0 of x into 2 to the power j by 2, but it is 1 because j is 0, into phi of 2 to the power j is again 1, so x minus k into dx. But as we know, x is also 0, so this also goes away and we are left with phi of x. Now we know how phi of x looks. It has its span from 0 to 1. So this is my phi of x and its value is 1 only between 0 to 1. So this integration will be 0 everywhere except from 0 to 1. So let's solve it for 0 to 1. F of x is x between 0 to 3. So it will be x into phi of x is 1 between 0 to 1. So it will be 1 into dx. This essentially means that this will be x square upon 2 and the limits are 0 and 1. So if you put x is equal to 1, what we get is 1 square, which is 1, that is 1 by 2, minus, when you plug in x is equal to 0, you get 0 by 2, which is 0, and that's why the first alpha value that we get is half, which is alpha 0 0. Now similarly, we can calculate alpha 0 1. Let's calculate alpha 0 1. Now j is equal to 0 and k is equal to 1 in this case. And the formula is integral running from minus infinity to plus infinity. We have f0 of x, 2 to the power j by 2 is 1, and then phi of x minus k. Now k is 1 over here, so it will be x minus 1 into dx. And we know how phi of x minus 1 typically will look. It will be a shifted version of phi of x by 1. So this is phi of x minus 1, and so it will last between 1 and 2. So this integral will run from 1 to 2. F of x will be x between 0 to 3. So this is x into phi of x minus 1 will be 1 between 1 and 2. So 1 into dx. So this will be x square upon 2 for this limit 1 to 2. And if you plug these values, what we get is, when we put x is equal to 2 square, which is 4 upon 2, so that is 2, and minus, you put x is equal to 1, you get half. So 2 minus half, which is 4 minus 1, and that is 3 by 2. So this is my alpha 0 1. I would encourage readers and viewers to confirm that similarly alpha 0 2 will be 5 by 2. So we got all the three alpha values, 1 by 2, 3 by 2 and 5 by 2, and it makes sense because it's a low pass filter, so it will calculate the average. So average over range 0 to 1 is half, 1 to 2 is 1.5, that is 3 by 2, and 2 to 3 is 2.5, which is 5 by 2. So it makes a lot of sense. Now let's plug those values over here. So the first value that we get is half, which is alpha 0 0, into phi of x, because k is 0, plus 3 by 2 into phi of x minus 1, plus 5 by 2 into phi of x, sorry, let me remove this. So it will be phi of x minus 2. And this is my representation of f0 of x, which belongs to a subspace v0. Now let's plot this on our signal. So this is our signal, and let's plot our f0 of x, and I will use blue color for f0. Now between 0 and 1 it is half. Between 1 and 2 it is 1.5. And between 2 and 3 it is 2.5. Right? So this is our f0 of x, which belongs to v of 0. All right. Now let's look at our objectives, and we are done with our objective number 1. Now let's move towards our objective number 2, that is to calculate g0 of x that belongs to w0. I will use green color for that, and g0 of x which belongs to w0. Now w subspaces are high pass subspaces, and they eventually give us all the details because it's a high pass filter that we make use of. And again z is equal to 0, so the window of operation will be 1 upon 2 to the power 0, which will be 1. That means v0 and w0, they both have window size of 1, no dilation at all. So the resolution is fixed, and the formula for g0 of x will be summation over all the k values. K values will once again run from 0 to 2 because window size is 1, and then we have beta 0k because z is 0, 2 raised to z by 2 is 1, and then psi of x minus k. So this is the formula for g0, and again we need to calculate 3 beta values, beta 00, beta 01, and beta 02. So let's do that now, and then we'll come back and plug those values over here. Let's calculate the first beta value, which is beta 00. And we know the formula, it is integral running from minus infinity to plus infinity, and then we have g0 of x into 2 to the power z by 2 is 1, and then psi of x minus k. Now k is also 0 in this particular case, so it will be psi of x minus 0, that is psi of x into dx. Now since we have used har psi of x, it typically looks like this. If this is x and if this is psi of x, then between 0 and half it is plus 1, and between half to 1 it is minus 1. So we'll have to split this integral into two parts, one running from 0 to half, and g0 of x is same function, so it will be x into psi of x is plus 1 in this half, so 1 into dx, plus the second half which runs from half to 1, and we have the same function x, and now psi of x is going to be minus 1, so x into minus 1 into dx. For this first part it will be x square upon 2, and it will run from 0 to half. And now I can take out this minus sign outside, and we can say that this will be x square upon 2 once again over the range from half to 1. And it's a simple maths that can be solved. So I would request viewers to please solve this and confirm that this will be minus 1 upon 4. And it makes sense because it's a upward moving function, and so when you take the difference between two consecutive points, obviously the difference will be minus because the next point is larger than the previous point. So this is one of the details. For when the beta value is negative, we can say that the function is upward moving. So this can be used for stock market, for example. If the details are negative, that means the stock is moving up. If the details are positive, that means the stock is moving down. And that's why the high pass filter brings out all the interesting details. That's what we say. I would request viewers to please confirm the remaining beta values, and these beta values will look like this. Beta 01 will also be minus 1 over 4, and beta 02 will also be minus 1 over 4 because the slope is consistent, and so the beta values will also be consistent. Then you can plug these beta values in the formula to calculate G0 of x. So beta 00, beta 01, beta 02 all are minus 1 by 4. So minus 1 by 4 psi of x plus minus 1 by 4 psi of x minus 1 plus minus 1 by 4 psi of x minus 2. So this is G0 of x that belongs to W0. Now using the same color, which is green, we will go back to our original function and superimpose this projection of G0 in W0 on top of our signal. So this was our signal, and we have already plotted F0 of x into V0. Now the first part is beta 00 into psi of x, and beta 00 is minus 1 upon 4. Minus 1 upon 4 into the first half of psi of x, which is plus 1. So between 0 and half, it will take a value of minus 1 by 4. So if I extend this, this will be minus 1 over 4 between 0 to half, and then plus 1 over 4 for the next half, and then again minus 1 by 4, and then plus 1 by 4, and then minus 1 by 4, and then plus 1 by 4, and again so this is G0 of x, which belongs to W0. I hope this is clear. Now let's revisit our third objective, and we can say that objective number 2 is achieved. Now let's calculate f1 of x that belongs to V1, and let me use a red color for that so that there will be no confusion. Now what we intend to find out is f1 of x that belongs to V1. Now since this is a V1 subspace, the kernel is a low pass filter. J is equal to 1. So the window of analysis is 1 upon 2 to the power j, which is 1. And so the window of analysis is half. Now since our signal lasts from 0 to 3, and now the window of operation is half, I will require 6 such windows to span the complete span from 0 to 3. So how many k values do we need? 0 to 5. So I can write down now that f1 of x will be equal to summation over all the k values running from 0 to 5 alpha 1 k, because j is 1, so alpha 1 k values, and 2 raised to j by 2. J is 1, that is 2 raised to half. In other words, square root of 2 into phi of 2 to the power j. J is 1, that means 2, and 2 times of x minus k. So this will be the formula for f1 of x. Now it goes without saying that we are talking about phi of twice x, and this is a dilated version. So this is where the dilation comes. This is where the resolution changes, and we will see how beautifully it unfolds. But let's calculate these alpha values first to get the feel of the process. And the first alpha value will be alpha 1, 0. Now j is equal to 1 and k is equal to 0. So let's calculate alpha 1, 0. So it will be integral from minus infinity to plus infinity, and then f1 of x. It's a projected same function projected in v1 into 2 raised to j by 2, that will be square root of 2, into phi of twice x minus k, but k is 0, that's why phi of twice x into dx. Now we already know how phi typically looks. So phi looks like this. It exists from 0 to 1. This is my phi of x, and it has a value of 1. So x runs from x runs from 0 to 1. Now what we are asking for is twice x. So naturally x would run from 0 to half, isn't it? And that's why this is a squeezed version. And although we are squeezing on the x-axis, we need not enlarge on y-axis just to maintain the area under the curve, because this particular factor over here is the normalization factor. So it takes care of that normalization. We will also see how this normalization factor normalizes all these alpha and beta values. But right now let's calculate the value. So we also understand that phi of twice x will look like this. It will be 1 only between 0 to half. And now this is my phi of twice x. So with this, let's calculate alpha 1, 0. So the integral would obviously run from 0 to half, because it is non-zero only in that range. F of x will be x into root 2 into phi of twice x is 1 in this range into dx. Let me bring out root 2, and then we are left with x square by 2 over this range of 0 to half. And now if I plug that in, this will be square root of 2 into, now if I plug x is equal to half, then square of that will be 1 by 4. And 1 by 4 into 1 by 2, so it will be 1 by 8. So root 2 upon 1 by 8. But we can also write down root 2 into 1 by 8 slightly different way. So it will be root 2 into 1 upon 4 into 2. And now this 2 can also be written as root 2 into root 2. So 1 root 2 gets cancelled out, and the same root 2 upon 1 by 8 can be written as 1 upon 4 root 2. You will understand the reason behind this very soon. So this is my first alpha value, alpha 1, 0. We'll calculate one more alpha value and then we'll move on. So let's calculate alpha 1, 1. So now j is 1 and k is also 1. So it will be integral running from minus infinity to plus infinity, and then f1 of x root 2 into phi of twice x minus 1, because k is equal to 1 into dx. Now we should remember that phi of twice x minus 1 is also equal to phi of twice of x minus half. So it is that dilated function, and we need to shift it towards right hand side by half. So if you plot it, it will be the shifted version of the earlier phi of twice x and by half, and so it will exist between half and 1 with a value of 1. So x-axis is x and y-axis is phi of twice x minus 1. I hope this point is clear. And if we plug that in, what we get is, so the integral would run from half to 1, and then f1 will be x into root 2 into 1 into dx. And I would encourage the viewers to solve this, and you will realize that what you end up getting is 3 upon 4 root 2. And now the trend is quite obvious. So the alpha 1 k values would typically be 1 upon 4 root 2, 3 upon 4 root 2, 5 upon 4 root 2, 7 upon 4 root 2, 9 upon 4 root 2, the last one will be 11 upon 4 root 2. So these will be the alpha 1 k values for different k values ranging from 0 to 5. I hope this is clear. And now if we plug this into this formula, what we get is f1 of x will be equal to, now you will realize why we said that root 2 is the normalizing factor. So alpha 1 0 is 1 upon 4 root 2 into root 2 into phi of twice x, plus the next factor is 3 upon 4 root 2 into root 2 into phi of twice x minus 1. And you can plug in the rest of the alphas. The root 2 gets cancelled, and as far as the projection f1 of x into some subspace v1 is concerned, these are the factors that we get: 1 by 4 and 3 by 4 and 5 by 4. Now let's plot these and let's superimpose these on the original signal that we have started working with. So this is the signal, and between 0 and half it is 1 by 4, and then it is 3 by 4, and then it is 5 by 4, and then 7 by 4, and then 9 by 4, and then 11 by 4. So you can clearly see this trend over here. And so this red representation is f1 of x, which belongs to v1. And if we revisit our objectives, you will realize that we have achieved our objective number 3. So third objective is also achieved. And now the most important one, and I will make use of yellow color for that. The last objective that we want to cross-check and validate is whether V0 and W0 actually gives me V1. We should also understand that for V0 the scope is from 0 to 1. So the window of analysis is from 0 to 1. For W0 the window of analysis is from 0 to 1, but for V1 it is half, 0 to half and then half to 1, and that's why we have to be little careful in doing this mapping. Now let's do this mapping by looking at the function and the projections that we have drawn superimposed on top of that. So if you look at the first window, that is from 0 to half. So for 0 to half, if we look at alpha 0 0, which is this blue colored line, and if we look at beta 0 0, the first half, which is this green line over here, then you will realize that alpha 0 0 the first half plus beta 0 0 the first half, it gives me alpha 1 0. It gives me alpha 1 0. How? So alpha 0 0 over here is half, and beta 0 0 over here is minus 1 by 4. So half minus 1 by 4, what we get is 1 by 4, and that is indeed alpha 1 0, which is depicted over here in red. And similarly, we can confirm this for every single window, and you will realize that this holds true, and this is orthogonal addition. And so in general, we can write when V0 is added orthogonally in W0, it results into V of 1. And this is a very important step. Have we realized what we have achieved? This is very, very important. So now we can say that the fourth objective is also achieved. And now just imagine you have V0 and you also have W0. You add them and together they will give you V1. Similarly, if you have W1, you add that into V1 and together they will give you V2. Likewise, you can keep going till V100 or V1000 or V10,000. And what will be the window of analysis for V10,000? The window of analysis will be 1 upon 2 to the power 10,000. So it will be that small, and that's why we can achieve the resolution of our desire. It could be very small window of analysis or it could be a very large window of analysis. And this is possible only because of the ability of the kernel to dilate. All the other conventional transforms, Fourier, Laplace, Z, they do not have this flexibility with their kernel, and that's why the dilation is not possible. And all of this discussion leads us to a very important equation. And this equation is what is known to us as dilation equation. So you can clearly see that in this dilation equation on the left hand side, what we have is phi of t, which is actually phi of 1 into t, and 1 is 2 raised to 0. So this is phi of 2 raised to 0 into t. In other words, we are saying that this belongs to V0. And on the right hand side, we have phi of twice t. So that is 2 to the power 1. And so we can say that this belongs to V1. We can write it mathematically correct this way, that phi of t belongs to V0 and phi of twice t belongs to V1. And so this very neatly captures that essence of underlying nested subsets. V0 is a nested subset of V1 and V1 is a nested subset of V2, and it continues as we keep moving up the ladder. We keep on adding up these details. This is a very unique equation. Why this is unique? This time is continuous time. K is discrete, and that's why we have summation. H of k is a discrete filter. So H of k is a low pass filter. So it can have coefficients like 1 by root 2 and 1 by root 2, for example. It's a discrete low pass filter. And again, this is continuous time, but k is discrete. So it's a combination of continuous and discrete values. And that's why we don't get such kind of equations in either Fourier or Z analysis. And that's why this is truly a unique kind of equation. In this lecture, I will not have time to get into why do we get such kind of an equation, but we have written a book on multirate signal processing if you want to know more about this equation and why in parts it is continuous and in parts it is discrete. please read our book, and probably you will be able to get better insight into this equation. So this dilation equation in a way captures the essence of the underlying nested subsets. So this is dilation equation for scaling function. Similarly, we can write dilation equation for wavelet function, which is psi of t. And on left hand side you have psi of t, which obviously belongs to w of 0. On right hand side you have phi of twice t, which belongs to v1. And once again, so w0 and v1, they capture the essence of w0, how it can be added in v0 then to produce v of 1. So this particular equation, the essence is also captured together in these two equations. So these two equations together, they very nicely capture the essence of this particular equation. Orthogonally, you add v0 and w0 and you move one step up in the ladder, that is v of 1. We also can think of similar constructs while moving down the ladder. For example, in this dilation equation, it is phi of t by 2, that is phi of 2 raised to minus 1 t. So this belongs to v of minus 1. And so we can also write down equation of this kind, v of minus 1, which is a subset of v of 0, v of minus 2, which is a subset of v of minus 1, and it continues. And this is a dilation equation for wavelet function. So psi of t by 2. So this belongs to w of minus 1 and this is v of 0. So together when we add v of minus 1 and w of minus 1, they give us v of 0. So this is a complete framework in nutshell. However, towards the end, we are going to understand that we need to accept this with a pinch of salt. And this word of caution emerges out of the fact that for the conventional transforms, the kernel is fixed, it is known, and that is it's a Gaussian kernel, it's a complex exponential. However, for wavelets, there are so many wavelet families, and which mother wavelet should be selected for what kind of application? It's a very challenging question, and one way of answering this question is by looking at the vanishing moments and figuring out the correlation. How? Let's quickly understand that and we will then conclude this session. We have already seen how Fourier transform works in the last session. So this concept of taking the dot product between the function and the kernel is not new to us. And then the dot product essentially gives us the Fourier output. Now in moments, what we do is we take the dot product between the function and the mth raised power of the independent variable. So this is function f of independent variable x, and when we raise this x to the power m, we say that this is the mth moment. We take the dot product and then we also take the integral in the range a to b. So a to b could be the range which is the range of non-zero existence of these two functions. So this is our definition of moments. And the fun part is all wavelet kernels de facto, they follow admissibility condition, that is the zeroth moment has to vanish. So the average of any kernel, wavelet kernel, is 0. For example, the simplest of all the kernels is Har, and we know that for the first half it is plus 1, for the remaining half it is minus 1. So when you take the average, it is 0, and we say that zeroth moment vanishes, so m0 is equal to 0. When the zeroth moment vanishes, the first order derivative exists. When the first moment vanishes, the second order derivative exists. When the third moment vanishes, then the third order derivative exists, which is the second moment actually. And that's why the existence of the derivative is also function of how many vanishing moments that particular mother wavelet has got. And I'm going to quickly share with you a case study from my own research. We are actually building this system for one of the giant company in mechanical field in Pune, and they had these huge rotating gears and they wanted to find out the cracks in the ball bearings, and we used to excite the system with known frequencies and then figure out what's coming back at us. Now, while sensing these frequencies back, the uh, reflected the reflected frequencies, they would mingle with each other and they would integrate, they would sum up with each other, and that's why even if there is a crack in the ball bearing, that discontinuity in the pattern would go unnoticed. So this is one example that we have constructed. This is g of t, and this is how g of t typically looks. Clearly it has jump at 0.5. So if you plot this function, the function looks like this. Right midway it has a clear cut jump. Now if we integrate this once, so if we integrate it once, we get h of t, and h of t looks like this, and it has a cusp jump at 0.5 midway. So if you plot it, it looks like this. So if you plot it, it looks like this, and it has a cusp jump. And now if you integrate it once more, so integration of h of t or double integration of the original signal, that is f of t, then it looks like this. And now if you plot it, it looks like this. So to the naked eye it looks like a nice smooth function, but we know that there is a discontinuity which is hidden right in between. And if we don't select the appropriate mother wavelet, then we may miss that discontinuity. So we have done the integration twice. Now in order to be able to figure out this hidden discontinuity, we have to select the mother wavelet that should be able to carry out the derivative twice. So the second order derivative should exist for that mother wavelet. For Haar or dB1, only zeroth moment vanishes, so it can carry out analysis of only first order derivative, and so Haar clearly misses this hidden discontinuity. We'll quickly see a MATLAB demo for this. So this is a MATLAB demo for finding out the hidden discontinuity in our signal. And as already discussed, these are the three signals G, H and F. H is the first order integral and F is the second order integral of G. And all these signals are then plotted, and eventually the last signal is also saved. So let's see how these signals they typically look. And as can be seen, the first signal has a clear-cut discontinuity, second one has cusp discontinuity, and the third one looks so smooth to the naked eye, and there is that hidden discontinuity which is not visible to the naked eye. And let's save this signal as test_sig_f.mat. So it's a MATLAB data file, MATLAB dat file, which is mat file. So it's saved as test_sig_f. And let me invoke the wave menu, which has now become wavelet analyzer. I'm still a little old fashioned. And let's invoke wavelet 1D. And in wavelet 1D, let's import the signal, load the signal that we have already created, which is that smooth looking signal, but we know that it has that hidden discontinuity. And now if we use Haar as the kernel for doing the analysis, then all the details and the approximation are shown over here. And even if you look at D1, and if I just zoom on the midway part, then you will realize the pattern is not disrupted. That means the hidden discontinuity was clearly missed out by Haar. And Haar and dB1, they are one and the same. So dB1 essentially gives us the same analysis, and if you zoom on to this part again, there is no disruption in the pattern, so the discontinuity is clearly missed and Haar was not able to find it. With dB2, now if I zoom on to the middle range, you will realize that in the middle portion you can see the pattern disrupted. So that clearly indicates that dB2 was able to find out this hidden discontinuity. And dB3 anyways has more number of vanishing moments, so it clearly finds it out. And as we keep going up with the filter and the filter length, the clarity with which the hidden discontinuity is captured is better. And thus we can conclude that more is the length of the filter, more are the number of vanishing moments, and higher order derivatives can be handled. And Haar couldn't figure out this hidden discontinuity because Haar only has one vanishing moment, only the 0th moment vanishes. So it can do the analysis only up to first order derivative. And all the other filters, DB2, 3, 4, they had more than 2 vanishing moments, so they were able to find out this hidden discontinuity. So the MATLAB demo clearly depicts that selection of mother wavelet is extremely important. So although wavelet transform, it has become very popular, and we see a lot of papers, a lot of researchers making use of wavelet kernels, we also have to be a little careful in understanding the maths beneath and carefully selecting the appropriate mother wavelet. I hope today's session was able to convince our viewers that if you understand the maths beneath, then you truly understand the zoom in and zoom out properties of wavelet kernel, and they're so powerful, then you'll be able to build many interesting applications around it. Due to time constraints, I won't be able to cover up the applications. However, like I said, please go through our book. We have given many examples, many illustrations, and many applications that can be built using wavelet kernels. Thank you so very much for your patient hearing, and I'll be more than happy to answer the questions from the audience. This video will also be available on Moodle, so if you have any questions, please feel free to post it on Moodle. Thank you. I appreciate your time.